This is section 9.4. I'm going to do this in two videos. The first portion is going to be normal form and solutions. The second portion is going to be quite a bit of theory, and I might do mixing problems, I might not. But they are on your lecture notes. So let's start with a review of what we did last time. Write x prime equals ax as a linear system where x is this vector and a is this matrix. So just like we did last time, let's start, that's very annoying, let's start with the matrix equation x prime, so that's x1 prime, x2 prime, x3 prime equals ax. So copy down a, 0, 1, 1, 0, 0, 1, and then write down x. All right, and to write that as a linear system of three equations, I'm gonna multiply this product out. So dot 1, 0, 1 with x1, x2, x3, and our top equation will read x1 prime equals x1 plus x3. All right, our middle equation will read x2 prime is x2 plus x3, and our last equation is going to read x3 prime is x3. And that's actually what we call the normal form of a linear system in three unknowns with three equations. So we've already started what we're going to talk about today. And then let's do B here. Write this equation as a linear system, then solve. So K1, I'm dotting out, K1 minus 2K2 is 1, and K1 plus K2 is 2. All right, in this case, one equation is not a multiple of the other, so we can't ignore either equation. So I'm going to do the elimination method. I'm going to subtract this equation from the top one. So negative 3K2 is negative 1. So that gives me K2 is 1/3. All right, and if K2 is 1/3, then K1, looking at this second equation here, is 2 minus 1/3, which is 5/3. So my solution is K1, K2 equals 5/3, 1/3. You can't clear fractions because there's no parameter, there's nothing free. There's only a single solution, it has fractions, and you're stuck with them. All right, the normal form of a linear system in n equations with n unknowns looks like this. If the f's are all 0, we say the system is homogeneous. If one or more of those f's is not 0, then we say it's non-homogeneous. So let's practice writing out linear systems in normal form. So write the system as a matrix equation. Are they homogeneous or non-homogeneous? So here we're going in the opposite direction from the first example we did. In this example, I had a matrix equation, I wrote it as a linear system in three equations with three unknowns. Now I'm starting with a linear system, I want to write it as a matrix equation. So to that end, I'm going to first rewrite y plus 5 as 0x plus 1 times y plus 5, and then 2x minus y plus 0. So the part that doesn't involve an x or a y goes into your f of t. So the vector form of the left-hand side is tx dt dy dt, which you can write if you want, shorthand, x prime, y prime. And then I want to write this just look at this part here, this is 0, 1, 2, negative 1, that matrix, times xy. All right, so make sure you see that. This is called the coefficient matrix, by the way. So when you dot out, you'll get 0x plus y and then 2x minus y. All right, and then the f of t vector is 5, 0. That's the part that doesn't involve an xy. So this would be my f of t. It happens to not have any t's in it. It's a constant vector, but that's okay. It still is the part that doesn't involve an x or a y. So this is non-homogeneous because the f of t part is not 0, 0. All right, so let's try another one. This one I don't have to rewrite. It's already in the form like my x is first, my y is in the middle, my z is third, and then my t's at the end. So all 3 rows look like that. So I can just go straight to the matrix form. This is x prime, y prime, z prime is the matrix. I just pick off the coefficients of x, y, and z. 6, 1, 1, 8, 7, negative 1, 2, 9, negative 1, times x, y, z. And then I add on the part that doesn't involve an x, a y, or a z. That's t, 10t, 6t. All right, and so that's my answer. And this is non-homogeneous because here's my f of t, and it's not the 0 vector. All right, why don't you pause the video and try C yourself. Okay, hopefully you did that. And you got x prime, y prime, z prime equals, let's write down, let's pluck off the coefficients, 1, 1, 1. The coefficient of x in the second equation is 0, so 0, negative 7, negative 1. And then 2, there are no y's, so put in a 0, and there are 9 z's, x, y, z. And then there's nothing that doesn't involve an x, a y, or a z. So this is actually a homogeneous system of linear differential equations because our f of t is 0. All right, so let's look at one more. Write the system without matrices as a set of scalar equations. So here we're going to go in the other direction, and we've got x is little x, little y. So let's just start out with writing out what this is as a matrix equation. It's x prime, y prime, this is my intermediate step, is 4, 3, negative 1, 2, x, y, plus, I'm going to distribute the e to the t, because I'm going to be combining in a minute, negative e to the t, e to the t. All right, and so if I want to separate this out into 2 equations, the top equation will read x prime is 4x plus 3y minus e to the t, and y prime, this is the second equation, negative x plus 2y plus e to the t. So again, that's a non-homogeneous system because our f of t is not the 0 vector. All right, so let's talk about solutions of systems. Again, some of this is repeat from last time. Write out the system x prime equals ax as a linear system. So once again, I got my intermediate step. X prime, y prime is a, which is 1353 times x, y. And that gives me x prime equals x plus 3y. Y prime is 5x plus 3y. Okay, so you should be able to go easily between these two different notations. Show that this x is a solution of x prime equals ax. Do not assume what you're trying to show. That's code for do left-hand side and right-hand side of this equation separately. We did one of these last time. So you might want to pause it and just do it yourself and make sure you can do that. Okay, so the left-hand side is x prime. We take the derivative, negative 2 e to the negative 2t, positive 2 e to the negative 2t. Right-hand side is ax, which is, a was 1, 3, 5, 3, and x is e to the negative 2t, negative e to the negative 2t. Multiply that out, we should get x prime. Let's just make sure. I'm dotting here. E to the negative 2t minus 3 e to the negative 2t is negative 2 e to the negative 2t. And then 5 e to the negative 2t take away 3 e to the negative 2t is 2 e to the negative 2t. So yes, these are equal. Left-hand side equals right-hand side. So again, we're just verifying we have a solution. In the next section, we'll be able to find these solutions ourselves. And given a solution, can we solve an initial value problem? Yes, we can. We did this last time again, so you might want to pause it, find C1 and C2 yourself. All right, hopefully you got negative 3/8 and 1/8 for C1 and C2. Here we go. We're going to plug in x of 0 is 0, 1, and that equals, so over here I put 0 in for t. So I get C1, 1, negative 1, plus C2, 3, 5. Distribute the C1 and the C2 and write down your two equations. That's C1 plus 3C2, and 1 equals negative C1 plus 5C2. So I will add these two equations together to eliminate C1. 1 is 8C2. So C2 is 1/8. And then C1, look at this equation. If C2 is an 1/8, C1 is negative 3/8. So plug that back into x. X is negative 3/8, 1, negative 1, e to the negative 2t, plus 1/8, 3, 5, e to the 6t. And you can leave your answer like that, or you can distribute into this vector here, negative 3/8, 3/8, e to the negative 2t, plus 3/8, 5/8, e to the 6t. We usually leave the e's outside, but you could also distribute those. And if you do that, let me go one step further. You got your big X, which is little x, little y. And that's the vector negative 3/8, e to the negative 2t, 3/8, e to the negative 2t, plus the vector 3/8, 3/8, e to the 6t, and then 5/8, e to the 6t. Okay, so that single vector equation is actually two scalar equations. If you read across the top, that's this equation here. x is negative 3/8. Oh, sorry. This is with the C1 and the C2 in it, what I have here. But yes, you can read across the top. This gives us x is negative 3/8 e to the negative 2t plus 3/8 e to the 6t. And little y, the bottom equation, 3/8 e to the negative 2t plus 5/8 e to the 6t. Those are parametric equations. So if you plot what a solution looks like, if you plot for different values of t, starting at negative infinity, going to infinity, what you're getting is this blue curve. So I plotted this parametric equation. And then I also showed the trajectories, which are solution curves, for just various values of C1 and C2. You get a bunch of different curves. But the curve we get from our set of initial conditions is the blue one. So that's how you can visualize a solution. Again, we won't find solutions till section 9.5. All right, so that's going to end this part of the video, and then I'll pick up and do the second half in the next video.